Hello again. It's December 28th, 2021 in the evening, and I'm Ken Eklund. And I was just watching another video, and I have to comment on it because I think it's incorrect. So I'll just let it play, and then I'll stop it and critique it.
Or are aware of the information in my general relativity videos that are already up on YouTube, and in particular that you're aware of two key points. The first is what is called the principle of equivalence, and what that says is that if you are in a box with no windows, then you cannot tell the difference between being in outer space and accelerating with an acceleration g, or being in the same box on the surface of the Earth, stationary, but subject to the gravitational force, which carries an acceleration g. There is no experiment, let's put you in the box, there is no experiment that you can do that will distinguish between those two situations. Now that is actually not quite true. The difference, of course, is that if you are in outer space, travelling with an acceleration g, then all parts of this box, including you, are accelerating at the acceleration g. If you are on Earth, then because the value of g varies according to the height above the Earth, the value of g at this point will be ever so slightly greater than the value of g at this point. And so there is a slight difference in the value of g in this situation. And if you can measure that, then you can tell the difference. That difference is called the tidal force. But apart from that, Einstein said that that was a principle of equivalence. You can't tell the difference whether you are accelerating at g or subject to a gravitational force, which is represented by the acceleration g. The second principle.
Okay, let me say something about the first principle. Well, it's wrong because, okay, this one's right when you're, well, except for the thing about, this being in a faster time, and this is a slower time. I don't know about that. But he got the gravity part right. There's a constant gravity force pulling him down. But they got this one totally wrong. If you're in a spaceship and you're taking off from Earth, you're going to feel G's because Earth's pulling you down, and then the floor's coming up. But once you're in space and you're moving along at the same speed the spaceship is moving, then you're going to feel weightlessness, and you'll be able to float around the cabin. I see what they're trying to say. Like, let's say the spaceship is stationary in space. There's no gravity around it, no planets around it. And then you start your engines. The floor will come at you, and it'll feel like gravity. And you might even be able to stand up. But once you get going along with it, and you have the same inertia that the spaceship has, then you're not going to feel gravity because you'll be in space away from any gravity source, and you'll just have the same inertia. But over here, see, the Earth is always there, so you're always going to feel the gravity. So this one is wrong, and the second one is wrong too.
Is that light bends in a gravitational field. This was Einstein's reasoning. If you take the person who is in the box that is accelerating through space with an acceleration g, and here is the box, and this time we're going to shine a light from this side of the box to the other side of the box. But of course that will take a finite time, albeit small. And if this box is accelerating with an acceleration g, by the time the light gets halfway across, the box will have accelerated a little bit further forward. So it'll now be here, which means the light will have reached that position there. By the time the light gets to the right-hand side, the box will of course have accelerated still further. And now the light, which of course is just going in a straight line, will reach here. So if you look at it, it appears within the box that the light has gone from here to a point lower down to a point even lower down. In other words, the overall impression is that the light has gone from here to here to here, and that's a curve. At least it should be if I've drawn it properly. So Einstein says, if that is what happens when you are accelerating through space with acceleration g, since the principle of equivalence says you can't tell the difference between that and being stationary on Earth subject to an acceleration g, then the same thing should happen in this scenario here, that light will appear to bend in a gravitational field.
Okay. Well, it doesn't appear that way. This is just like a magic trick. It kind of reminds me of, these are the three walnut shells, and you got to guess where the P is. And I see, because I drew a picture of what I think it would look like. It's either a magic trick or they really believe this stuff. But wow, I don't know, man. All right, so let's say you just shot a couple photons, and they're heading out here, and then the box moves up. These are the same photons, and then you shoot some more. Then the box moves up. Shoot a couple more. These photons would be here, and then on and on. They would keep going straight. They're all going straight. And okay, you have this line here. You could, if you're a physicist that believes in Einstein, you could draw a line here and say the light went from here down to here. And maybe it's even a curve, because we're going to say that gravity pulled it down, like it was going out in this direction and gravity pulled it down, so it had to curve. So it's actually a curve. It's not a straight line. If you were a physicist, you could, you were probably taught that, and you could repeat that. But if you think about it, the light would behave this way. It's always going in a straight line. So there's no curve. There's no, gravity's not affecting it. What did I write here? I wrote the photons are traveling straight. Not curving. Because they confuse these physicists. They want to idolize Einstein, so they confuse separate photons with, they'll call it a beam of light. A beam of light, and then they can say the beam is bending. I don't know. I don't really get it, but anyway, they're wrong. It would not. It does not do this. They don't. The one from here doesn't. See, because the photons shot from here, they weren't shot from this position over here. They weren't shot from this position. They were shot out from this position up here. So they're, that's where the trick is, because they're saying that this is like one beam, and it appears to do this, like make a curved thing down, but it's just light. It's light just traveling all in a straight line, moving across. As the boxes move up, the box moves up. And now the next thing, now they're trying to say, because gravity bent the light down and curved the light, now they're going to say they can prove gravity bends light because they can see because of this sun experiment that's coming up
Now, of
next.
course, he could have been wrong, but in fact this was shown to be true during a solar eclipse. What happens during a solar eclipse is that the moon essentially blocks the sun, so that from the Earth the sun, as it were, is blotted out. And what was noted from the position on Earth was that they could see a star just slightly to the right of the sun. But they knew, astronomers knew, that that star actually was located behind the sun, and it shouldn't have been possible to see it. And the explanation was that what was actually happening was that light from that star was being bent in the gravitational field of the sun and then coming to us on Earth, giving the impression that the star was here, when in fact the star was really here, but the light was being bent in the sun's gravitational field. Now, here was the problem for Einstein. Newton's law of gravitation, which everybody had thought had served us well for so long, says that the gravitational force is equal to the gravitational constant times the mass of one body multiplied by the mass of another body divided by the distance between them, r squared, or divided by the distance squared. And that's fine, except that in this situation here, light is bending in a gravitational field, but photons of light have no mass. So these two mass terms, well, at least the sun has mass, but the photon doesn't. So this form of Newton's law doesn't work if it is going to apply to light. Photons have no mass.
Okay, I'm going to stop it here. I heard one physicist, a new guy, he's just coming up with his own ideas. He says this experiment was flawed because they didn't consider that the sun has an atmosphere. So what happened here in this experiment was that the light shining from the star reflected off the atmosphere of the sun, or somehow reflected, or maybe it was bent, could be bent, in like a lens type of situation. So, and then that's why we could see that star from Earth. It didn't have anything to do with the gravity, because so Newton was probably right, but then Einstein had to come up with his own thing, so he came up with some just wild, totally wild stuff. He started saying that um, his space and time stuff, the light was bent because it was following the space-time grid, which is like, yeah, right. Try to prove that.
So Einstein came up with a completely different approach to gravity. Instead of there being gravity, he said, actually what is happening is that all forms of motion are represented by movement in curved space-time.